we're going to jump into muscle mechanics, and a couple of items that are important when we talk about muscle mechanics are the fascicle arrangement as well as the principles of leverage. There are a couple of factors which are going to contribute to the force of the muscle as well as the speed with which that muscle can react, and those will be the arrangement of the fascicles as well as what type of lever muscles are. With regards to how fascicles are arranged, there are several relatively common patterns which are listed there. When you talk about circular muscles, you're talking about fascicles that are going to be arranged in concentric rings. We'll talk about orbicularis oris and orbicularis oculi, which are muscles around the mouth and the eye, respectively. Convergent muscles have a broad origin, and the fascicles are going to converge towards a single insertion. Classic example of that is pec major, pectoralis major. Sometimes you have the fascicles running parallel, which form strap-like muscles. Classic example of that is going to be sartorius. And then occasionally you have fusiform shaped fascicle arrangements, which basically just means they're going to be spindle-shaped muscles that are having parallel fibers. And really a classic example of that is going to be biceps brachii. Please be careful when you are listing muscles or naming muscles on any of the homework or any of the assessments. We have two biceps in our bodies. We have the biceps brachii, which are associated with the upper part of the upper extremity and flexion of the elbow. And we also have biceps femoris, which will be part of the hamstring group. We also have a pennate arrangement of fascicles. So they're going to be relatively short fascicles that are going to be connected obliquely to a central tendon that runs the length of the muscle. And classic example of that guy is going to be rectus femoris, which is going to be one of the quadriceps muscles. I would never ask you about the three forms, but there they are if you have a burning desire to know. And this shows you each of the fascicle arrangements that we have just discussed. So why do we care? Because that will determine the range of motion of the muscle, which means basically the amount of movement that the muscle has as it shortens. It will also determine the power of the muscle. When you have long fibers that are much more parallel to the long axis, they can shorten more, and generally they are not terribly powerful. The power of a muscle is going to depend on the number of muscle fibers. So the bipennate and the multipennate muscles have the greatest number of fibers, so they don't shorten much, but boy, are they powerful. Let's jump into levers since we're talking about muscle power and speed. This can be fairly complex, and if you spend enough time with it, it certainly becomes easier. When you talk about lever systems with regards to the muscles, you need to remember that the skeleton provides a series of levers around which skeletal muscles contract. And I know we've said that before. So those bones act as levers. The lever is going to be a rigid bar, in other words, the bone that is going to move on a fixed point, which is known as a fulcrum. And in this case, we're talking about a joint. The effort is the force, which is supplied by muscle contraction when we're talking about the muscular system, which will be applied to the lever to move resistance or the load. The load is the resistance. So bone, tissues, any added weight form the load in this case. And that load has to be moved by the effort. So why do we care? Because levers are going to allow any given effort the ability to move a heavier load or further or faster. There is some speculation that if you had a long enough lever, you could actually move the Earth relative to the moon. At least that's the theory. This will depend on what's known as the fulcrum position relative to the load and relative to the effort. So we have a couple of items that we need to talk about, which include the mechanical advantage. So if you have a load that is close to the fulcrum, the effort is far from the fulcrum, and a very small effort can move a large load. When you talk about a mechanical disadvantage, and you're talking about a speed lever, the load is going to be far from the fulcrum, and the effort will be close to the fulcrum. So the load is moved quickly over a fairly large distance, and you have, in essence, a greater range of motion. So this gives you some information about levers. You see the effort, you see the fulcrum, you see the load, and classic example is jacking a car up. I will not ask you that equation. We're going to buzz through the rest of this, and I'm going to tell you exactly what you need to know. So that shows you a mechanical disadvantage with the speed lever. So I rarely, if ever, put a lot of questions about levers on the assessments because you actually need to spend time learning the muscles. When you talk about the basic principles of levers, and this is more for clarification than anything else, if the effort is further than the load from the fulcrum, the lever is going to operate at a mechanical advantage. If the effort is nearer than the load to the fulcrum, the lever will operate at a mechanical disadvantage, and you're talking about a speed lever. We have three classes of levers, which are going to depend on where the effort, the fulcrum, and the load are placed. For the purposes of this course, if you want to know about the type 1 and type 2 levers, that's great. First class lever, that shows you an example. You can see where the load is, you can see where the fulcrum is, you can see where the effort is. An example of that will be moving your head into a position of hyperextension. You also have second class levers where the load is between the fulcrum and the effort. So think wheelbarrow, think pointing your toes and standing on them. And it shows you what's going on there with the fulcrum, the load, and the effort. And an example of that is when you are contracting your gastrocsoleus complex and standing on your toes or the balls of your feet. And you need to know this absolutely positively. I guarantee you that questions about what type of lever most muscles are on assessments. All right, so the effort is going to be applied between the fulcrum and the load, and most skeletal muscles are third-class levers. Let me repeat that. Most skeletal muscles are third-class levers. I would absolutely positively know that if I were you. We've already talked about speed levers, which means that you're losing force, but speed and range of motion are prevalent. You talk about power levers, you have slower and more stable movement, and these are going to be used where strength is really important. Again, most skeletal muscles are categorized as third-class levers. So when you talk about a third-class lever, you have a load, you have the effort in the middle, and there's the fulcrum. Tweezers are a classic example of that, as will be the contraction of biceps brachii when you're talking about flexing your elbow.